Welcome back to ECE 501B. Homework number 5 is due tomorrow, I believe, the 30th of October. Then shortly thereafter on Monday, homework number 6. So I'm hoping you're already sort of working on both of those simultaneously. Our exam number 2, is a week from today, and that will be focusing on Material Sense Exam 1 and up through the topics in homework number 6. That's the idea. And I'll maybe try to flesh that out a little bit more, but I hope homework 6 may not yet be on Graham-Schmidt, but I might sneak that in to exam 2. I'll think about that. Give me a weekend to think about it, but you can be thinking about those topics in terms of material. And I think that's homeworks 4, 5, and 6, roughly, since exam number 1. We are moving forward beyond that today, and hopefully, as you can see, scrolling up from the bottom, I would like to start in chapter 7, maybe, before we finish today. But let's try to finish up chapter 6. We will recap by reminding ourselves that we started to play with linear functionals, and really instead of thinking about, oh no, another new thing, we've already talked about it. It's really a linear map. It's a linear map that now the codomain is really just scalar. So instead of going from, let's say, R4 to R4 with a linear map, we're now going from R4 to R. Or we're going from R4 to, or let's say C5 to C. We're now mapping from some vector space into the scalars. That means we're doing this linear functional, and if it's a linear functional, it has to, or if it's a linear map, it has these additivity and homogeneity properties that have to be satisfied. Once it has that, then we can discuss or introduce what we talked about last time, where we can identify a vector W, build one up that will be an inner product of our general vector V or U with that W. That's the linear functional, that we can create this phi sub U as an inner product, and we can build up W. We will then remind ourselves about the adjoint, which is T dagger, so I may just say T dagger, and that sort of pushes you back into the space that you came from. It's not really an inverse, but it's something similar. You go, let's say T is a linear map from V to W, T dagger, the adjoint of T, is a map from W to V. That's the adjoint. We'll show that the adjoint map is in fact linear, and then we will look at this result that compares or shows relationships between range space and null space of these maps and their adjoints. Meaning the null space of the linear map T is equal to something related to T dagger, etc. And we'll show that. Then we will talk about or look at matrix representations of these maps, and we'll actually show that under certain conditions we can think of the linear map T being represented as a matrix A. If we want to find the matrix representation of T dagger or the adjoint, that becomes the complex conjugate transpose of A. That's going to then finish chapter 6, and then we will get into chapter 6 was inner product spaces. So how do we now get distances and angles? Then what did we do before? Once we had sort of the playing space, we started thinking about maps, and then we specialized those maps to be operators. We'll now start looking at operators on these new energized spaces, which are inner product spaces. So they're vector spaces with an inner product, and now let's talk about operators on that, or in that domain. And that will then lead us naturally into self-adjoint operators. So now you have a lot more dinner talk table, what do I want to say? Table talk with your friends. You can start talking about self-adjoint operators. And they're going to go, wait, let's change topics. Let's talk about something. No, this is fun. Let's talk about self-adjoint operators, which really means the linear map and its adjoint are the same. And that provides us with nice properties. Here's the linear functional recap. Linear functional, again, is just a linear map. It's just now we are focusing that codomain, or sort of the result of that linear map, into the scalars. So we start with some vector space, and the linear functional just means that we are using or having a codomain that is only scalars. So we could start with some 8th dimensional vector space. A linear functional takes a vector from a vector, in quotes, from that vector space and maps it to the scalars. That's a linear functional. And we learned last time that we could actually build up an inner product that would produce the result of the linear functional applied to, let's say, some arbitrary vector u. And that was theorem 645. Given a linear functional, linear is critical, on a vector space V, then there is a unique vector W such that u, whatever that, for all u in our vector space V, inner product with this unique W produces this linear functional phi on u. That's what we learned from theorem 645. And if we've defined these e's, e1, e2, e sub n, as the orthonormal basis on the vector space, then we can generate this unique vector W by looking at these complex conjugates of this linear functional applied to each of those basis vectors, weighting or scaling those basis vectors, and that's W. And that phi applied to these different basis vectors is really sort of saying, how are these orthonormal vectors aligned with this linear functional, in a sense? That was theorem 645. That allowed us then to talk about a new entity, a new object called an adjoint, which is inspired or results from having a generic linear map T. If we have a linear map T between two vector spaces, V and W, then the adjoint of T, which we were calling T dagger, is a linear map between W and V. And T dagger is defined so that these inner products, illustrated this way, are equal. Meaning we take a vector V in our domain, in our original domain, and map that through the linear map T. That will produce a vector in the vector space capital W. We take the inner product of that result with W. That will give us a number. That gives us a scalar. Real or complex, typically, is what we're dealing with in our scalars. That now needs to equal V, inner product with T dagger and W. That's how we actually define the adjoint operator, is through this inner product. Question?
Is there any connection between this W and the W in theorem 6.45? I'm wondering, I guess, because it says for all three, I'm wondering how the T.
So now the question is this W related to the W in theorem, whatever that was, the previous theorem, 645? I don't remember what the theorem was, but no, they aren't. So this W is a generic W. Any W you find in capital W needs to satisfy this inner product. So W now can be anything, but you pick one. Usually it's sort of variable, and you then allow that to determine what T dagger is, so that T dagger operated on a W gives you the same inner product when you take that inner product with V and TV inner product with W. So those W's, maybe I should have called it something else, but I think this is sort of the textbook notation. But that W is not necessarily this W that's still on the screen. Okay? We'll look at more examples of these adjoints in a minute, but let's just see if we can start to understand some of the properties of the adjoint. So sort of keep this relationship in mind, and we will eventually, I hope, build up some T daggers given a T. But let's just look at what we can find property-wise just from this definition. So first, let's just see if we can answer the question, is the adjoint a linear map? And that's not a poorly drawn T, that's actually a dagger. Is that clear? So that's T raised to the dagger, that's the adjoint. And if T dagger is a linear map, what do we know about linear maps and the properties that they have to satisfy or have? So it basically is superposition, isn't it? It's additivity and homogeneity. And if you combine those, it's like this superposition property. T of alpha 1 V1 plus alpha 2 V2 is alpha 1 T V1 plus alpha 2 T V2. A lot of times we separate those and just show its additivity and its homogeneity are true. So let's break it up into two pieces and say, okay, if it is a linear map, then we have to have additivity and homogeneity. If we look at the additivity piece, then let's just start with this inner product. TV in the first slot and this sum of two vectors, W1 and W2 in the second. And now we can rewrite that as the sum of two inner products using the additivity of the second slot. This now can be written as TV W1 plus TV W2. That was the, let's say, additivity of second slot to produce that equality. But now let's go back and replace, since we know that TVW by definition has to be V comma T dagger W, let's apply that twice to the right hand side, which means that this needs to now be equal to V T dagger W1 plus V T dagger W2. That is just the definition of the adjoint. That's all we're applying there. Now we have two inner products, the sum of two inner products, and the first slot's the same. We can do the additivity of the second slot again, and we now have V with T dagger W1 plus T dagger W2. But what do we know that the original left-hand side needs to equal. If we, again, apply our definition of the adjoint. If somebody gave you this inner product on the left-hand side of TV, comma, W1 plus W2, if you invoked the definition of the adjoint, what would that have to equal? Is everybody okay with that? So the comment from the classroom was we simply T-dagger the second slot and remove T from the first slot. That's how we've defined the adjoint. And that now means if we compare the second slot, since the first slots are the same, in the far right-hand side of what we developed, with what we know the left-hand side needs to equal by the definition of the adjoint, we can now equate the two second slot pieces, or now we can conclude that T-dagger W1 plus W2 is equal to T-dagger W1 plus T-dagger W2, and that's the additivity that we were trying to show. Questions on that? Yes. So now the question was, and I may have to be reminded, what do we mean by injective? So the question is, did we have to know that the inner product was injective? And what did we mean by injective? T of V equals. So I'm saying that we have now shown that these two inner products are equal and that the first slots are the same. So that must mean that the second slots are the same. Yes, so now what we are basically saying is if these inner products are the same, then yes, so I'm now concluding or making the statement that if the first slot is the same and the inner product's the same, then I'm saying that the second slot pieces are the same. That's what I'm assuming. Okay, and if that's the case, then we do have these this additivity of the adjoint. Okay, so now let's look at homogeneity. This is now saying that we have TV AW, and if we now want to slide that scalar on the second slot outside the inner product, what does it become? It now gets conjugated, doesn't it? So we now have this result by the conjugate homogeneity of the second slot. Then, if I leave that A star outside and now just use the definition of the adjoint, this now becomes is that correct? So now I'm just invoking in this second row or second line just the definition of the adjoint. Now let me push that scalar back inside the inner product and let me go ahead and put it into the second slot. And what do I need to do to that scalar to put it into the second slot? Conjugate that. So now I have V A star T dagger W. And I conjugate that again to give me that. Is that okay? Just checking to make sure you guys were still awake. Because I take my glasses off and I can't see if your eyes are open or closed. All right. So now we're going to do the same thing that we did before. We now have, what do we know has to be true about the left-hand side? Or what is the left-hand side equal to if we invoke the definition of the adjoint? What's in the second slot? T dagger applied to what was originally in the second slot. Is that true? That's the definition of the adjoint. And now if we are allowed to make the connection with the second slot, if that's now okay, which is what I'm assuming is true, then T dagger of AW is equal to A T dagger of W. And that's the homogeneity. Okay? Which now says that the adjoint is a linear map. It satisfies those two properties, which is additivity and homogeneity. In general, if T is this linear map between V and W, then T dagger is a linear map between what? W and V. Now, we can write down some properties that the adjoint satisfies or has. So the adjoint has the following properties. One is additivity, which is if we add up two linear operators and take their adjoint, what's that going to be equal to? Just the sum of the adjoints, which is what you would have anticipated. So that's one property, and that's true for all S and T, and those are both linear maps between V and W. We also have conjugate homogeneity, meaning if we now look at a scaled version of a linear map and take its adjoint, then that's going to equal the complex conjugate of that scaled linear map times the adjoint. And that's true for all A and T. Another property is the adjoint of an adjoint. Meaning, if I now take the adjoint of T, I get back the original linear map. A fourth property is the identity property. If I have an identity map and I take the adjoint, what would you think that would be? It's just the identity map, isn't it? And now if we do products, we've done additions, now if we do products, this is sort of like what you're used to seeing with inverses. Now you have T dagger, S dagger for all, and now let's say T is a linear map from V to W. What's S? What vector spaces does it map between? S is now W, not necessarily V, is it? Now it can just be some other vector space. It could be, let's say, U. Meaning if you now have two linear maps and you sort of concatenate those or cascade those, T could go from V to W, and now you have another linear map applied to the result of that first map. The first map resulted in being in the vector space W. Now you go into something in U. Now you would have to keep track of what those adjoints map to, but you essentially have to make sure that if you applied the adjoint of ST to ST, you better get back. Did we derive that anywhere? Maybe we didn't, but now you are sort of working on this similar property like we've worked on with inverses, or what you're familiar with matrix inverses, or the product of inverses. Now, let's look at some more interesting relationships. Or useful. Between these null space and range space of the original linear map T and its adjoint. And this is now proposition, whoops, we haven't gone back to the polynomial chapter. So we're still in chapter 6, 646, okay? So now if T is a linear map from V to W, then we have the following relationships between these different subspaces. The null space of the adjoint map, T dagger, is actually related to the orthogonal complement of the range of T, or the range of T perp. So if you know something about the null space of the adjoint map, now you know the vectors that are in the orthogonal complement of the range of T. Those are equal. And we can say, establish other relationships. We can say that the range of T dagger, where can we get to through this linear map T dagger? Well, we'll get to the same place as when we looked at the null space of T's orthogonal complement. So if we have the null space of the linear map, then we find its orthogonal complement, and that will actually tell us where we can get to from T dagger, or applying T dagger. And we can also say that the null space of T is the orthogonal complement of the range space of T dagger. And finally, the range of T is the orthogonal complement to the null space of T dagger. Let's look at and see if we can convince ourselves that some of these might be true. Let's look at the first one. So now we're looking at vectors that live in the null space of T dagger and seeing how they are related to the orthogonal complement of the range of T. Which means if we know what's living in the range of T, or if we have that, then the inner product of those with these vectors better give us something like 0 for this orthogonal complement. First, let's pick a vector W that belongs to the null space of T dagger. So now we're picking a vector that lives in the null space of the adjoint map. What does that mean about T dagger W? It's 0, isn't it? That's by definition. W is in the null space of T dagger, then if we operate on that vector W with the adjoint map, it better give us 0. Let's now say that we have the 0 scalar, and that's true, isn't it? Any vector V in the vector space capital V, inner product with the 0 vector will give us 0. But now let's take that 0 vector to be this T dagger W. Since T dagger W is 0, we can now say that this now implies that V T dagger W is equal to 0 for all V, all vectors little v in capital V. Questions on that? Now, what's our definition of the adjoint? If we apply the definition of the adjoint to this inner product immediately above where I've opened up this angle bracket for a new inner product, what does V comma T dagger W need to equal by definition of the adjoint? T applied to V equaling or inner product with W. So that must be 0. And that's also true for all V in V. But what does that say about W and that vector in the first slot? What's the vector in the first slot represent? These vectors in those first and second slots are orthogonal, aren't they? Or they're perpendicular. And what are the vectors in the first slot? What's one way of denoting those? That's the range of T. Anything that, for all V mapping through T, we're going to populate the range of T. And now we've just found that W is orthogonal to that, so those W's are in the orthogonal complement to the range of T. Therefore, W is an element of the range of T's orthogonal complement. But where did we start with W to begin with? W was in the null space of T dagger. And now we've concluded for every W that's in the null space of T dagger, we've now shown that that's in the orthogonal complement to the range of T, so that now those two are the same.
Sorry, I had a hard time. Where do you think the saying that W is the range of T?
Okay, so let's now go back and see if I can try to rephrase that. The question was, I didn't follow your argument for why did W end up being in the orthogonal complement to the range of T. Is that the question? So why is W an element of the orthogonal complement of the range of T? Or another way maybe of thinking of that is, what does W being in the orthogonal complement of the range of T mean? That means any vector in the range of T, inner product with W will be 0, and that's what we tried to say up above. So now we say we have the range of T being created by TV, and now that vector W is orthogonal to it. And that's basically the definition of the orthogonal complement, or the perpendicular subspace. Let's look at, is that okay? So now we've shown the first piece of that connection of the adjoints and the linear map T. And in particular, if you now find a vector that's in the null space of the adjoint, you can also claim that that's orthogonal to the range of your original linear map. So now when we're saying the range of T, we're saying any linear combination of vectors that will, or that you can get to by mapping through this linear map T. That's the range of T. The range of T is where can you get to in the codomain by going through this linear map T. And we've now found vectors that are orthogonal to everything in that subspace, the range of T. Let's look at the third one. Let's look at the third one. So now, if we look at the third relationship, it's very similar to what we just did. The third relationship is now the null space of T. We can find vectors v that live in the null space of T, and now we need to show that those are the same as the orthogonal complements to the range of T adjoint, or the adjoint of T. So now let's pick v to be a vector in the null space of T, and that now says that we can state that TV is equal to 0 if v is in the null space of T. Again, we can say 0w is equal to 0 for all 0 vectors, and we've just found a particular 0 vector that we like, which is TV. And that's true for all w in capital W. Again, let's apply then the definition of our adjoint. That now says that if we have TVW, the definition of the adjoint says that that's equal to V T dagger W. And now we've just said that that's 0 for all omega in capital, all W in the vector space W. And what does that say? Now V is orthogonal. And what is that T dagger W giving us? Vectors that are generated by T dagger W are in the range of T dagger, aren't they? So now we're saying that V lives in the orthogonal complement to that space. So now we're saying that V is an element of the range of T dagger's orthogonal complement. And now we have, if V is orthogonal to the range of T dagger, it's also in the null space of T, is what we're saying. And that's, I think, what we started with respect to statement 3. So now we can say that the null space of T is the same as the orthogonal complement to the range of T dagger. And if we take the orthogonal complement of both sides of 2 and 4, we should get back to ones that we've already shown. Meaning, if you look at 1 and now take the orthogonal complement of 1, or I, you'll get 4. Is that true? And if you take, and so we showed 1 was true, so the orthogonal complements of 1 should be true. That's 4. If we now look at the last one that we just proved, which was 3, and we take the orthogonal complement of that, the left-hand side of 3 becomes the right-hand side of 2, and the orthogonal complement of the right-hand side of 3 becomes the left-hand side of 2. So those are the same. What I'm saying is by showing or proving 2 and 3, we have actually shown all 4 because we can take orthogonal complements of both sides of remaining entries completes the proof. Okay. Now let's look at these matrix representations of these maps. And we'll find that there's a useful relationship between the matrix representation of a map and the matrix representation of its adjoint. And this is actually proposition 47 in chapter 6. So now I'm getting a little bit sloppy maybe, but A is now an orthonormal basis. A is, let's say, A sub 1, which is a vector, A sub 2 is a vector, A sub 3 is a vector, not coordinates of a vector, but vectors themselves. If A is an orthonormal basis on V, and B is an orthonormal basis on W, then the matrix representation of T dagger, whoops, between, or with B being the basis on the domain of T dagger and A being the basis, the orthonormal basis on the codomain of T dagger, the matrix representation of that linear map, T dagger, is the conjugate transpose of the matrix representation of T with the basis vectors just reversed. Showing that gets a little bit messy in terms of notation, so I'm going to tell you to look at the textbook for that. See Axler for the proof, because I think it's better if you sort of work through that yourself instead of me trying to put it up here and you're going, doesn't look right, or it looks confusing. Check the book for that, but let's just now remind ourselves what we mean by conjugate transpose. The conjugate transpose of, let's say, a matrix A, B, C, D, E, F. Notationally, we might denote that as A, B, C, D, E, F, complex conjugate transpose, turns into what? We could transpose it, which just means the rows becomes the columns or vice versa, and then we conjugate each of the elements. So now if we transpose it, are we okay with that? And now we conjugate each of the elements inside that transpose. So now this is A star, D star, B star, E star, C star, and F star. If somebody now wants to take the conjugate transpose or the transpose conjugate of a matrix, you transpose the matrix and conjugate all the elements. That's what we're meaning. So what we're saying is if we find a matrix representation of our linear map T, and somebody says, give me the matrix representation of its adjoint, now you just do the complex conjugate transpose of the original matrix, and that's now the matrix representation of your adjoint. That's the nice thing about the adjoint. In words, then, the transpose of, or one way of saying this is you transpose the matrix representation of T and then take the complex conjugate of each entry. Or if you start with the other, if you start with the matrix representation of the adjoint, you can find the matrix representation of the linear map by doing the complex conjugate transpose. Let's look at some adjoint examples, as I had promised before. And let's say that we begin with a linear map T between C3 into C3. That's now T. So that suppose that the linear map T of x, y, z is now we need to find three coordinates. The first coordinate is 2x plus 1 minus I, y. That's the first coordinate of our linear map T. The second coordinate is 3 plus 2ix minus 4iz. Again, these are just scaled multiples of the original coordinates, x, y, and z, somehow making up the new coordinates after the linear map. And our third coordinate is 2ix plus 4 minus 3iy minus 3z. And what we're asked, let's say in this particular example, let's say we want to find T dagger. What's the adjoint of this linear map? So now it's easier, exactly. The comment was, let's find the matrix first, and then we can complex conjugate transpose that matrix, and then from the matrix we can find what the adjoint linear map looks like. Is that clear? Let's now then, for the solution, I don't know if I can squeeze this in before it scrolls off the screen. The solution, let's first find the matrix representation of T. And we'll call that A. What does that look like? What do we need in order to build up the first coordinate in our codomain? Or how big is A as a matrix? What's the matrix representation of this linear map dimensionally? It's 3 by 3, isn't it? We're going from C3 to C3. Do I have a non-zero entry in the 1, 1 entry of A? You have 2 entries in that? I'm teasing. 2, the number 2, right? So we have to scale x, then we scale y, and we don't scale any z. That gives us now the first row, or the first coordinate of our codomain, or the output of operating on xyz with the linear map T. The second row of A. This isn't so bad, is it? And now we can build up the last row. That's 2i, 4 minus 3i, and minus 3. Is that okay? Now we can find the matrix representation of T dagger, which is simply the conjugate transpose of A. I'll do the hard part. Right? So the transpose of the diagonal is the diagonal, and I can conjugate those pretty easily. Then the 1 minus I in the 1, 2 entry jumps down to the 2, 1 entry conjugated, and the 1, 3 entry comes to the 3, 1 location, and that was 0. What's in the 1, 2 entry of my blue matrix? What about the 1, 3 entry? Everybody okay with that? How come I didn't get that? Is that correct? So it needs to go a little bit different place, doesn't it? It needs to go a little bit different. But now what goes up in the 1, 3 entry of the blue matrix? It's going to be populated by the transpose of A conjugated. The transpose of A is 2i, and we conjugate it, it's minus 2. Is that okay? Now, where does that minus 4i belong? In the bottom, in the second column, doesn't it? And we conjugate it, so it's now 4i there. And the original 3, 2 entry goes to the 2, 3 entry conjugated, so that's now 4 plus 3i. Is that okay? Now can we build up or write down the linear map associated with the adjoint of T? So if I said, let's operate on a vector, x, y, z, a 3 vector, with the adjoint, what is in the first coordinate of that result in terms of x, y, and z? Did everybody follow that? Then we have the second coordinate, which is 1 plus I times x plus 4 plus 3i times z. And finally, we have no x, 4i y minus 3z. And that was, you could, I guess, just by inspection write that down if somebody gave you that, right? It's maybe not so easy to see that the adjoint of that original linear map is now this. It was probably easier to process by finding the matrix representation of the linear map, finding the complex conjugate transpose of that, and then putting that into this linear map notation. Questions on that? Well, that was kind of fun. Let's do a different one. Maybe this one will be, well, it'll be a little different. I was going to say something about its difficulty, but I always sort of set myself up when I make something like that, some comment. Suppose T, a linear map, is now between, say, R3 and R3. And suppose that we're given that T of x, y, z is 2x plus y, 3x, and 4y minus 3z. And we want to find the adjoint map of T. We can use the same process that we just used, can't we? We can find the A, which is, let's say, the matrix representation of that linear map. What are the dimensions on A? Again, it's 3 by 3, isn't it? What's in the top row of A? Second row? Third row? Did we do that right? Does that look okay? Just taking that linear map T into its matrix representation. Is that okay? Now we have A star transient, or I'm sorry, transpose, which maybe I would just shorthand A dagger. If we now do the complex conjugate transpose, we get 2, 3, 0 in the first row, 1, 0, 4 in the second row, and 0, 0, minus 3 in the third row, which allows us now to say that T dagger of x, y, z is now 2x plus 3y x, whoops, plus 4z minus 3z. Is that okay? So that's a way of finding these adjoint maps. If somebody gives you a linear map, you now can confidently find its adjoint. Let's show that these two sort of inner products are the same as far as V T dagger W being equal to V or TV comma W from the definition. So now let's say that T is mapping between V and W, and suppose that we now let a vector in the domain be 1, 1, 0, and we're using now these linear maps. We're still doing example 2. So now let's say that V is 1, 1, 0 and W is 0, 1, 1. And we want to now compute TVW. This shouldn't be hard. It's basically just, yes. So the question was, why did I pick these two vectors? We don't have that much time for me to answer that. It took me days to find these two vectors. I'm teasing. These just came out of the blue, okay? I just snatched these. I just grabbed these from space, okay? So there's no real significance. It's just that, are these vectors orthogonal to each other? Are they? Not really, are they? But so if you took the inner product of V and W, is that what I called them, V and W? What's the Euclidean inner product of V and W? Okay, so now the inner product is going to be, what's the result of an inner product? It's a scalar, isn't it? So now it has to be a number, just a scalar. And if I said, what's the inner product? How are these two vectors aligned? Do they sort of share any kind of direction? Are they correlated in any way? And yes, they do somehow sort of. One is in the XY plane and one's in the YZ plane, aren't they, as far as vectors? So they do share some commonality. They're not orthogonal. So they're not zero, but they are some correlation. And in this case, they are 1, aren't they, for an inner product? Well, that was a long answer. I did sort of expand on that. But no, I just pulled these out of the air. What is TV inner product with W? Well, we now just have to go back to the matrix representation of T. To produce TV, we just have A times V, and that's not 2. So TV, we can think of now as this matrix A, 2, 1, 0, 3, 0, 0, and 0, 4, minus 3, 1, 1, 0. And do we remember how to multiply matrices and vectors? 1, 1 is, so I really picked these to be easy to play with. Hitting a matrix in the back with 1, 1, 0 is just saying take the first column and add it to the second column and forget the third column. That's really what 1, 1, 0 is saying. 1, 1, 0 is saying just combine this first column with the second column. Don't worry about the third. If we simply add up those first two columns, we obtain 3, 3, 4. Now if we take the inner product of TV with W, that's now the inner product of this 3, 3, 4 with 0, 1, 1. And that's 7. Let's now compare that with the inner product of V with T dagger W. And let's do the messy part first, which is, let's say, T dagger W. That's now this 2, 3, 0, 1, 0, 4, 0, 0, minus 3, 0, 1, 1. Again, because of the nice property of these vectors that I picked, that I spent hours trying to build up these vectors. No. But now I simply add up the last two columns of that A dagger matrix. And that's definitely not what we had when we had TV, was it? 3, 4 minus 3 is not 3, 3, 4. but we're not going to scale or take the inner product of it with the same thing that we had before. We now take V with T dagger W. Or we're now taking the inner product of 1, 1, 0 with 3, 4, minus 3. And what is that? 7, which is what we better have obtained. Questions on that? Now that we have some of these ideas of adjoints and linear maps, we can now start to talk about operators on inner product spaces. Which is chapter 7. And we can actually begin with this concept of self-adjoint operators, which really just says that an operator, T, and remember what an operator is? That's just a linear map from the vector space back into that same vector space. So we can just say T is an element of this L of V, that's enough, is self-adjoint and if you really want to inspire a lot of conversation at your dinner table, you can say, oh, we were working with Hermitian maps. It's also called a Hermitian operator, or T is Hermitian if T is equal to T dagger. Having T equal to T dagger imposes some constraints on the elements of the linear map T. This imposes certain constraints on the matrix representation of T. For example, the matrix representation of T, dimensionally, what is that if it's an operator? Dimensionally. It's n by n, isn't it? Or it's square. So the matrix representation of T must be square. And you know that why. So now you've put on your 2-year-old hat. Why? So now we know that operators in general, aren't they? They have to be square to map from the same space back into the same space. So T is square. Operators must be square, which says that T is going from V to V. And B is if we have the matrix representation of T in general, let's say it's n by m, that generically is not the same dimensionally even as the matrix representation of T dagger, which could be m by n. So these are generically, just talking about a linear map and its adjoint, we've just seen can be different shapes. And if we start, let's say the matrix representation of T is, let's say, A, B, C, D, E, F, G, H, I, and I is not the square root of minus 1, it's just a variable. What is the matrix representation of T dagger? In general, just the matrix representation of T dagger, it's the conjugate transpose, isn't it? So now look at the conjugate transpose of T, which is the matrix representation of T dagger. That's supposed to equal the matrix representation of T. That imposes certain constraints on those elements. See if you can just do that, and we'll pick up at that point on Monday.